Hi everybody. I'm glad to be back here with you all again. If you're able to print the notes packet, that's great, but if you can't, that's okay too. You're gonna need notebook paper and or a spiral notebook would be fine. So you don't have to write down every single word, but just the equations, the definitions, any section that you think is important. As we go through the notes, I'm going to highlight certain problems that I definitely think are important for you to do. So just keep note of that. Feel free to pause anytime you need to. There's going to be times where I'll pause and ask you guys to try a couple problems on your own, and just look out for that. Okay, so all right, let's begin. Okay, so today we're going to be talking about section 8.1, which is solving linear systems in two variables. So this process includes graphing, elimination, and substitution. Okay, so for the following warm-up problems, we're going to rewrite each equation in slope-intercept form first, and then we're going to graph each line. Okay, so a system, just to kind of start out with a definition, is always going to be two or more equations. Okay, so this first system has y equals 3x. And if we look at that equation, it actually is in slope-intercept form. The b value is just 0. So we have y equals 3x plus 0. That means when I'm graphing, the y-intercept is 0, and the slope is positive 3. Or we could write that as 3 over 1. So that tells me I'm going up 3 over 1, up 3 over 1. Okay? And so now we're going to take a straight edge. I'm actually going to go and grab a straight edge. And we'll connect those points to create that line. The more points you can put on the graph, the better. It just gives you a more accurate line. Okay? So now we're going to take a look at the second equation, which is not in slope-intercept form. So what we want to do first is move the x over to the other side. We've got 2y equals negative x minus 14. And to get y by itself, we divide by 2 to cancel that out. So that leaves us with y equals, now looking at this fraction, we have a negative 1 over 2. So that's negative 1/2 x. Dividing here, we get negative 7. So my y-intercept is negative 7, right there. And my slope is going down 1 over 2, down 1 over 2. Okay, now in an effort to get this line to continue the other way, I can go up 1, left 2, up 1, left 2, and now I've got my line. Now it says to write the ordered pair of the point of intersection. So if we're looking at this intersection point right over here, it's negative 2, comma 1, 2, 3, 4, 5, negative 6. Now it says here to check the solution by plugging in the point into the original equation. Okay, so we're going to plug, and actually this is in both equations. So we're going to plug in negative 2 in place of the x and negative 6 in place of the y. And you'll notice you get a true equation. That tells us that that point works. Now we also want to plug the point into the other equation. So I have the x value plus 2 times the y value. And is that equal to negative 14? Well, here we have negative 2 plus negative 12, and that is equal to negative 14. Okay, so we just found that the solution of this system is the point that both of the lines have in common. Forgot to highlight that. Okay, so now I want you guys to take a minute, see if you can rewrite both of these next two problems in slope-intercept form and graph them both in order to find the intersection point. I'm going to pause the video. So you'll notice here that the solution for this system is at 2, 5. It's the point that they both have in common. Now, this checking portion over here, you're not actually going to need to do that. But what I was just showing is that if you plug it in to both equations, they are both going to work. Okay? So a system of linear equations in two variables, x and y, consist of two equations, and they're usually in what we call standard form. Now, you noticed before that some of the equations that we saw up above were in slope-intercept form. That's fine too, okay? So really our main definition for a system is that there are two or more equations, okay? So most of the time, if they are in standard form, they're gonna look something like this. Now, a solution of a system of linear equations in two variables is an ordered pair that satisfies both equations. So what that means is when you plug them into both equations, they both are true. So when its system is graphed, there should be two lines, and they should intersect at a point, which is the solution. And I should say that sometimes we're going to graph these lines, and notice that there's this word here, should. They should intersect. Sometimes the lines don't intersect. And we'll talk about that in a bit. Okay? So once you're ready, go ahead and flip to the next page. Okay, you'll notice there are two practice problems for you guys to try. I'm going to give you guys a few minutes. Go ahead and see if you can try at least one of these problems, okay? Now, you'll notice there are graphs here. If you weren't able to print out the notes packet, try to draw a nice coordinate plane with even tick marks. That way you'll get a solution that's nice and neat, okay? So I'll give it a pause right here. All right, so if you guys look at the work that we did for these two problems, you'll notice that when I got this first equation into slope-intercept form, we have some fractions here, that's okay. 1/3 I'm not really worried about because slopes, you know, they're pretty easy to work with in fractions. This number here, 5/3, I just put it into my calculator. So I knew my y-intercept was about 1.6, and then I went up 1 over 3, up 1 over 3. Okay, so that would be that first line. Now, when I try to get the other equation into slope-intercept form, you'll notice it's the exact same line. Okay, so what that means is my second line sits right on top of the first. And you can kind of see that I have those double arrows on each side. So we say here that there are infinitely many solutions because when I have one line that sits right on top of the other, they always intersect. Okay, so there's not just one intersection point, there are infinitely many intersection points. Okay, now what happened in the second equation, first one's in slope-intercept form, pretty straightforward. The second one, notice that it has the same slope, but a different y-intercept. So I graph these lines and you'll notice that they are parallel. And so parallel lines never intersect, meaning we have no solution. So that tells us that when two lines are parallel, there is no solution to the system of equations. Okay. Likewise, when two lines are the same, there are infinitely many solutions, which matches our example number 3. Okay. Now the last thing with graphing I wanted to show you guys was going to be the steps for using your calculator to find an intersection point. So I'm actually going to use the problem that was on the front page, and I'll just write it off to the side here. So we'll call this example number 1. And I'm going to write the two equations down. We had y equals 3x, and the slope-intercept form of the second line was -1/2 x minus 7. Okay, so I just want to show you guys what that looks like when we put it into our calculator. So I'll put this over here. I know that most students don't have the Inspire, so you guys can just read that on your own if you need to. Okay, so we're going to go into y equals and type both equations in. 3x -0.5x minus 7. I find it's easier to type in 0.5. And we're going to hit the graph button. And you'll notice we have a couple lines over here. Now your grid marks might look different. You might have a standard zoom. So my guess is most of you guys have a graph that looks like this. Okay, that means it's 10 by 10. Now I'm looking for this intersection point. Instead of eyeballing it, you can hit second trace, so that's our calc button. And we're going to go down to number 5. It says intersect. And we're just going to hit enter 3 times. And you'll notice that the intersection coordinate pops up right over here. So we have -2, -6. And if you look at the problem we did on the front, that was the solution. Okay, so if you ever are allowed to use a calculator, you should definitely use it to at least check your answer to see that you did it right. Okay? All right, let's flip to the next page. Now, solving a system algebraically is a process that I hope that you guys are familiar with. You guys should have done this in Algebra 2, probably Algebra 1 as well. I'm going to skip over these warm-up problems. We don't need to reiterate any of that graphing. So with substitution, we use this method when one of the variables is already isolated, or when it's easy to get one of those variables alone. So you'll notice if you look at both of these equations, I've got a plain x by itself. That tells me substitution's possible. Over here, I've got a plain y, no coefficient. So it would, we'd have to do some rearranging, but we can get that y by itself. So the process says to solve one of the equations for one of the variables. So let's start with this first example. I'm going to try to get this bottom x by itself. So that means I'm going to subtract 2y to move it to the other side. Okay? Now, the second step says to substitute the expression from step 1. So we're going to substitute this whole section into the other equation for the variable. So because x is equal to -2y plus 2, we're going to plug it in. We're substituting in the equivalent value of x. Now I still have a plus 4y equals -4. Now you'll notice that there's only one variable here that we need to worry about. So we can go ahead and solve. Combine like terms. Move that 6 over. Divide by -2. And we get y equals 5. Now that's only one of my variables. Remember, our solution should be an ordered pair. So right now, I know that the y coordinate is 5. But I need to plug it back into one of the equations, either equation is fine, to solve for the other variable. So I'm just going to plug it into this simplified equation because we're already almost there. So I plug the 5 in place for the y, and we have x equal to -8. Okay, so our final answer is this coordinate right here. So I'm going to give you guys a minute to try the next problem. I'm going to start working through here. I'm going to move the 2x over. Divide by -1. And I get y equals 2x plus 4. Now that quantity is going to get substituted in place of y in the other equation. You never want to substitute back into the original equation. So I'm going to plug it in. So we've got 4x minus 2 times y, and that's equal to 8. So notice y, and this all was represented by y. So we can go ahead and solve here. So we've got 4x minus 4x minus 8 equals 8. Now something interesting happens here. I've got 4x minus 4x, that cancels. And I'm left with only -8 is equal to 8. Now you might say, well, that's not true. This is not a true, scribbling there, not a true equation. That means we must have no solution. Okay. So sometimes you'll get something that's not a true equation. That's going to mean no solution. Okay, so if you do get a true equation, let's just make some space down here. If you get a true equation, let's say 5 equals 5. But the x's canceled out. We're not able to solve for x, or we're not able to solve for y. That means we're going to have infinitely many solutions. So the reason why in both of these examples we chose to use the substitution method, it was because we were able to pretty easily isolate one of the variables. Easy to isolate a variable. No coefficient. If for some reason all 4 of these variables had coefficients in front of them, sometimes it's difficult to use substitution. So we would need a second method in order to solve. And that second method is called linear combinations. Now, the other name for this is elimination. So we use this method when we can eliminate a variable. So the first thing you want to do is make sure both equations are in standard form. So we have that here in example 3. Now what we're going to do is multiply one or both of the equations by a constant to obtain coefficients that differ only in sign for one of the variables. That means, let's say one of the equations has it plus 2y, the other equation would have to have minus 2y. So you're looking for the same number in front, but one's plus and one's minus. Now, if we're looking at this first set of equations, let's say we want to eliminate the x's. It's really our choice what we want to eliminate. So if I want to eliminate the x's, I can turn this 2 into a -4 just by multiplying both sides of the equation by -2. Now it's important that we're multiplying both sides because the equation has to stay balanced. Now let's distribute through and see what happens. So I've got -4x plus 8y equals -26. And actually, let's just draw a line here just to kind of separate. I'm going to rewrite the second equation right underneath it because we didn't do anything to change it. And you'll notice that now I have -4x and +4x. So we're ready to move on to step 3. That says to add the equations. Combining like terms will eliminate one of the variables, and we're going to solve for the remaining variables. So I'm going to draw a line and put a big plus sign here. So when I add these two x's, I end up canceling them out. -4x plus 4x eliminates. Adding these x's, 8y minus 5y, gives me 3y. -26 plus 8 gives me -18. And so now I'm able to pretty easily solve for y. So I end up with y equals -6. Now in order for us to find the x value, we're just going to substitute it back in to one of the equations. It doesn't matter which one. Let's do the bottom one. 4x minus 5 times the y value equals 8. 4x plus 30 equals 8. And we're just going to get x by itself. So I think that's -22. Double checking my calculator. Yep, that's right. Divided by 4. I'll use my calculator for that as well. And I get x equals -5.5. Decimals are perfectly fine. So when we write our final answer down, remember that the x comes first and then the y. And there we go. So I'm going to have you guys try the next equation by eliminating one of the variables. You guys can press pause at any time. Okay, so hopefully you guys had a chance to try that problem. Let's multiply. I'm going to eliminate the y's here just by multiplying the second equation by 2. If I rewrite the first equation up top, didn't do anything there, multiplying everything by 2 in the second equation, you'll notice that your y's are going to get eliminated. So when I add these two equations together, I have 5x is equal to -3. divide by 5, divide by 5, x equals, we can either leave the fraction, I'm going to write it as a decimal, so we get negative 0.6. So at this point, we can plug this back into one of the equations. So let's plug it into the bottom. We've got negative 0.6 minus y equals negative 5. Add the 0.6 over. Use your calculator if you need to. And we end up with y equals 4.4. So we get this coordinate, negative 0.6, 4.4. Now for both of these systems, we decided to use linear combinations, again, also known as elimination, because we were able to multiply we'll say one of the equations in order to eliminate a variable. And so that's a summary of our first section, 8.1. What you guys can do, if you flip to the next page in the notes packet, I included the homework in there. I also uploaded the homework as a separate PDF into Google Classroom, so you can use that one as well. If you have the printed copy, feel free to just do the work on here and upload it when you're finished. Otherwise, you can do it on a sheet of notebook paper and just take a picture and upload that. That would be perfectly fine, okay? So this homework is due by the end of the day, Tuesday night, before midnight. Hope you guys enjoyed this video lesson, and if you have questions, please contact me during my office hours. Thank you.